Okay, so this actually wasn't so bad, but actually now I can walk around the room and do this. I'm not tethered anymore. Normally I actually have a cable so that I don't run on batteries, but in this particular case I don't, so I don't know where it is. So today's lecture 4. I noticed that some people are doing the homework, and I hope that people are enjoying it. It's due again tonight. In terms of our reading, you should have already read this at this point. So some of what we've talked about today should be reviewed, but there's also you should also read chapter 3. The slides must not have been updated properly. Anyway, read chapter 3 as well. We're going to start hopefully talking about chapter 3 today. Homework is due tonight. So in terms of a review, so we have, everybody should at this point be very familiar with these relationships. These are the entropic relationships. These equations should become pretty much second nature to you if you want to be successful in this course. And another set of equations that should be second nature to you are these ones. If you have any questions about them, either mathematically or intuitively, you can ask me about them now, or you can post a comment in the discussion board, but basically everyone should be familiar with them. We also discussed this Venn diagram, which I think actually allows one to fairly quickly come up with most of the relationships that we're interested in, as long as you realize that this quantity in the center can sometimes be negative. But if you sort of acknowledge that, realize that this is sort of a reasonable sort of first approximation of how one can sort of easily remember the relationships between all these quantities, which, and there are a lot of relationships. We also talked about the log sum inequality, which was in some sense, generalization of Jensen's inequality, and how it gave us some nice properties of the dimensional information in terms of its convexity as a function of either the marginal distribution or the conditional distribution. So we have, in particular, that when we think of the dimensional information as a function of the marginal distribution, which is this little guy down here, the marginal on x, then we're concave in that marginal. And then when we fix the conditional, and then when we think of it as a function of this conditional, this little conditional here, we're convex in the conditional fixing the marginal. So concave in the marginal fixing the conditional, convex in the conditional fixing the marginal. And that's going to be very important for doing various forms of optimization. Now today, the first thing we're going to start, any questions about that? So that's a review at this point. Data processing inequality. Now we can have a little fun. So let me ask you a question now. Let's say we have an information source. And the question is, maybe there's some additional processing done to that source, and maybe some subsequent processing done to the source. Is it generally possible that more processing, and by processing I mean any mathematical function or any algorithmic function or anything you can do to that information source, is it possible that processing can add more information about the original source than what was there before processing? Can we learn more about the source by studying it more, at least the information that we've got? So let's use this as a picture. So we've got an information source here, right? And there's some amount of information there. So that there's the entropy or something, and we have, let's say, some imperfect observation process. So we observe it. We have sensors, we have cameras, pictures, video, whatever, radar, and we observe some information in random variable y, and then we do additional processing. And this could be very, very computationally expensive. It could be solving an NP-complete problem. It could be doing anything you want. But any further processing, and we've got a new, essentially processed amount of information. And the question is it possible for z to tell you more about x than y tells you more about x? So before you answer that question, let's think about the following scenario. Image denoising. So everybody has a digital camera. Can you raise your hand if you have a digital camera? Okay. There's a big market for image denoising. So you take an image with your smartphone or your pocket camera, and it ends up being fairly noisy, and part of the reason why digital cameras work is because algorithms, image processing algorithms or computer vision algorithms, do something to the image to reduce some of that noise. Okay? In particular, high ISO images are very, very noisy. When you take images in low light and you boost up the ISO, the noise is going to be very high. That's also true of analog, of old film cameras as well. And so you use image denoising to remove the noise from the image and recover the original image. So here's an example. So here's a picture. There's an amount of information, which is the original picture. You have an imperfect observation process, which is the camera sensor, which is maybe like this. And we get a noisy version of the image. I don't know if you can see it being noisy. But then we do some image denoising, and we get back the refined original image. So, when you look at this, you can say, oh, well, that obviously looks more like the original than the noisy version. So therefore, I've recovered information about the original. Right? So then the question is, if this is X and this is Y and this is Z, does this mean that Z has more information about X than Y does? What do you think? Can it be that Z has more information about X than Y has?
But isn't that more like semantics? Maybe it appears more natural to us, but that doesn't mean that it has more information.
Well, it depends what we mean by information, of course, right?
Yes.
So, it's about the semantics of information, but we're still sort of in this semantics game a little bit, I think, right now. And of course, since this is information theory, you can then maybe make the function or make the question a little bit more refined and specific by saying, okay, well, let's say it's mutual information and entropy. Our measure of information in this class is going to be entropy, and the question is then, is it possible that the mutual information between Z and X can be greater than the mutual information between Y and X? So we can eliminate semantics and be very, very precise about what we mean by information in this class and answer that question then. What do you think? You probably shouldn't be able to. So that's what essentially the data processing inequality says. Unfortunately, we can't do this. So essentially, this is the way we set it up. So we've got our Markov chain. X, Y, and Z form a Markov chain if basically Y renders X and Z independent. So that's equation 4.2. So that means that we have the following factorization properties, that we can actually factor the distribution either this way or this way. Okay, these are standard conditional independence. And we can actually use Bayesian networks to describe a Markov chain. One way would be to write it in sort of temporal order in this fashion, or we could write it as sort of a outward going edges or a reverse time Markov chain. All of them essentially describe the same relationship between the set of random variables X, Y, and Z. They're all Markov chains. And a couple of other instances of a Markov chain is, let's say that Z is some function of Y. So let's say this is true and Z is a function of Y, then this actually forms a Markov chain. Why? Because Z is a function of Y and it's not a function of X as well as Y. In other words, if you know only Y, then you get Z. It doesn't matter. F can be random or deterministic. The key is random, and what we mean by random, but we mean independently random, independent of X. So let me make sure that that's clear. So it can be random as long as it's independent of X. And, or deterministic, it doesn't matter. X is irrelevant. And just as a notation, whenever we say X goes to Y, goes to Z, this is just sort of an implication. It just says this is a Markov chain. We're not saying X implies Y. We're just saying X, Y, and Z are in the relationship of a Markov chain. That's what this means. That's a statement. So there should be no confusion about that. So the data processing inequality says if X, Y, Z form a Markov chain in this way, then we must have that the mutual information between y and x can only decrease when we do further processing, the mutual information between z and x. So z can only have less information, or the same, or can at most have at most the same information about x that y has about x. Okay. So it can be random deterministic, and we can do all sorts of stuff. So basically this says that in our entropic form, as we perform further processing of a data source, we move away from it in a Markov chain, we can only, if anything, we can only lose information. So somehow, when we do image denoising, we've lost information about the original source, even though to us, somehow, it looks better. Now, in practice, what's really true is that what these algorithms do is they make assumptions about the statistics of real-world images. And they say most images, in all probability, we have, at least from looking at the noisy image, we have some information about what kind of image that is. And most images of say, people don't have purple and blue splotched colors all over the place in random locations. So it basically makes assumptions about the kind of image. But on the other hand, one could essentially put a noise film in front of a person and take a picture, and that would be the original image, a random noise film. So you don't actually improve information, but you're making assumptions. You have a prior, and most image denoising implicitly or explicitly have some prior about what real world images look like. A very famous example is a prior called total variation. For those of you who do a little bit of image processing, you probably know about that. How do we prove this? So let's actually prove it. Can everybody still see the screen? Remember, I'm trying to resist closing the blinds when it's sunny because it's actually so rare here that I like having the windows open. But the chain rule of information says that the following. There's two ways of actually writing the chain rule of information. We can actually write it in this way, where it's the mutual information between x and y, and then x and z given y, sort of the residual information, or it's the mutual information between x and z, and then x and y given z. Those are the two chain rules that we know. Now, if it's a Markov chain, x is independent of z given y. So that basically means that this part is 0. Right? And so we also have that everything else is non-negative because mutual information is non-negative. And so we have essentially this relationship. We have that this part here is greater than or equal to 0. So it must mean, therefore, that we have our result. I mean, it's a very simple proof. Just using non-negativity and the Markov chain property. So let's give a couple of examples of what this recovers. What if x is equal to y? So what if x is equal to y? What do we get? Sorry? Well, if x is equal to y, we get the mutual information between x and y is equal to 0? It's equal to the entropy of x. Right, it's not 0. Right, if these guys are equal, if the random variables are equal, there's still information. In fact, there's perfect information. Right? You get complete entropy reduction. In fact, in mutual information, how much does y tell you about x? Is everything. It tells you everything there is about x. And since it's equal to y, it's also the entropy of y. So it's the reduction. Remember, this is really important. This isn't clear. Mutual information is reduction in entropy. If x isn't equal to y, how much does y reduce the entropy of x? Well, everything. It reduces it by all there is to know. But in any event, in this context, if x is equal to y, we get the mutual information between x and y is equal to h of x, which is greater than or equal to the mutual information between x and z. Right, so, I mean, in some sense, we just get, I wouldn't call it a tautology, but we get back an inequality that we already know. That basically the entropy of x is greater than or equal to the mutual information between x and anything else. This is an upper bound. Okay, so that checks. What about another one? What if it was the case that entropy of y given z is equal to 0? So this means that if we know z, we know y. So that means that that further processing we've done to get z loses nothing about y. So intuitively, what must this say about this inequality? If we've got x as our information source, we get a noisy version of it at y, we do some further processing which loses no information. What can we say just intuitively about this inequality? Anybody? Well, it should mean that, z has lost nothing about y. So if z has lost nothing about y, this should be inequality. This should be inequality. Why? Because, if we've got z, we certainly have y, so therefore we have not lost any further information about x. And let's make sure that this is true. We go back to the definition. We've got a Markov chain so that this guy is equal to 0, right? Normally this thing, here, this part, normally this is greater than or equal to 0, right? But if given z, y is known, what is that mutual information quantity? So if you know z, if knowing z tells you everything about y, if you know everything about y, can knowing x tell you anything further about y? No. So therefore, that mutual information must be. There's nothing more about y we can learn. How much reduction in entropy is there on y? Remember, mutual information is reduction in entropy. So if I know everything about y, given z I know everything about y, can the entropy be reduced? No, because the entropy is already 0. Think of it this way. This guy is equal to h of y given z minus h of y given x and z. This guy's already 0. Right? This guy's greater than or equal to 0. Conditioning reduces entropy so that the whole thing has to be equal to 0. So therefore, this whole thing on the right-hand side of this case is equal to 0, and we have that this is equal to this. Right? So if this is not clear, then you need to review it. So I'm saying you should become very familiar with both the mathematical and the intuition. So sometimes, these are very intuitive quantities. The information theoretic quantities they're really, they behave just like you want an information function to behave once you get used to them. Even before you get used to them. But then you still have to guide your intuition. Your intuition has to allow you to go back and prove something about it. You can't just use intuition and say that's true. Like if if each of these things are true, you have to say, well, given that they're information functions, I think something should happen, but we should verify by using the properties that we've already proven. Okay, so another thing we get is that, there's nothing special about going to the right. I always say that on the northern hemisphere, everybody likes Markov chains that go from left to right. In the southern hemisphere, people like Markov chains that go from right to left. So if you go to Australia, everybody writes their Markov chains this way. Isn't that true? Do we have anybody from the southern hemisphere here? There aren't that many people I meet from the southern hemisphere. So the chain distance decreases information. This is an interesting question, which I'm not going to answer now. But the question is, imagine now a Markov chain that's more than 3 time steps, but it's a whole chain. So as you keep marching down the Markov chain, information is decaying, or certainly not increasing. How fast? What's the slowest that it could possibly decay? All these kinds of questions become interesting. But in general, as you're marching down a Markov chain, you forget the past. You can only forget the past. Just like societies, right? Now, there's a corollary that if z is equal to f of y, then we have this Markov chain. So therefore, this is just essentially saying the same thing. It's like if we do any function of y, where this function, if it does have randomness, it's independent of x. If it's deterministic, anytime you process y, you're reducing the information about x. That's something that we will use. And this can be any function. Right? It could be a vector-valued function. This function could return a whole vector of random variables. Doesn't matter how many of them there are, you're not going to get any more information about x.
And did you use this to prove that permutations on random shuffle?
That's right. That's right. That was the property that I used. You're right. I should refer back to that. Recall the random shuffle experiment. That was probably. I should have waited to represent that, but I think that's an important example. So. That was from lecture 1, right? Or maybe it was lecture 2. I don't remember. Okay. So, processing can only lose information about x. For those of you who are interested in machine learning or pattern recognition, this basically means that, if you have a signal source like an image or a cell phone tower signal and you're trying to recover the original message, the more processing you're doing, the less chance you're going to be able to get to recover the information, to recover the original message. So there's real world implications of this. Audio restoration. There's another corollary that if x and y and z is a Markov chain, then conditioning on z reduces the information that x and y have about each other. So remember we said that in general there's no relationship between the conditional and the unconditional mutual information. In the Markov chain case, there is a relationship because in this Markov chain case, knowing z means that there's less information than x can tell you about y. And we saw the extreme example was when the conditional entropy of y given to z was equal to 0, then this thing turns into 0. We can prove this very simply by in general, by just writing this expression this way. So this is the expression for the conditional mutual information. This is the expression for the unconditional mutual information. And we just get this from the Markov chain property. So, so knowing z, the intuition is knowing z reduces the amount of information left between x and y. So here's I don't know if this is a good example. But x is it's raining outside, y is the ground is wet, and normally maybe raining outside would tell you a lot about the ground is wet, and the ground would tell you that it's raining outside. But if worms are all around on the sidewalk, then the ground is wet tells you less about it raining outside. It's an everyday example that you think about all the time, of course. Everybody's sitting very symmetrically today. Seems everyone is sort of uniformly distributed. Symmetrically and uniformly distributed. Okay, so we've got the data processing inequality. And we have the other thing that we saw. Remember we saw this last time, that if x and y together cause z, that the conditional mutual information is greater. And we have this, for example, when x is independent of y, but when z is the sum of x and y. So this is another example how the conditional and the unconditional mutual information in general have no bound with respect to each other. It really depends on the particular setup of the collection of random variables. Or you could think of it as sort of the underlying causal relationship between the variables. Okay, any questions about data processing inequality? Okay, so has anyone heard this before? So the entropy of the universe is always increasing, and so at some point our universe is going to essentially become this sort of gray, uniform void where nothing interesting is happening, right? And that's sort of a current theory of thermodynamics. And how does this relate to our notion of entropy? The first law of thermodynamics is basically conservation of energy, basically that when you consider all types of energy transformation or energy transfer, that includes the amount of work done and heat and all this other stuff, that when the system is isolated, the total amount of energy is conserved. And the second law of thermodynamics is that of entropy. Remember, entropy is energy transformation. So basically, the total amount of entropy in an isolated system cannot decrease. It can only increase. So everything can only become, whenever there's some sort of energy transaction, the total amount of energy, the total amount of entropy increases, and hence, in this isolated system, it can only become more uniform. And the depressing fact is, of course, in the universe, then if you think of the universe as an isolated system, the overall entropy is only increasing. So entropy really, in some sense, means, in this particular context, sort of the availability of energy. And I have some pictures. So like which system has more entropy, the left or the right system? Right, the right one has more. And it has more unavailability. I think I said availability. I meant unavailability. It has more unavailability of energy, or less availability of energy. Whereas on the left-hand side, there's a gradient, and so therefore one can do work, potentially. There's less entropy on the left side. There's less potential energy. There's a temperature gradient, and there's uneven distribution. There's a smaller amount of entropy. On the right-hand side, we have more entropy. It's the same overall amount of energy, which is the first law of thermodynamics. There's less usable energy, however, uniform temperature, and so on and so forth. And here's the temperature distribution. It's uniform. Okay. And every time there's a transaction, every time you use energy in a closed system, hot mixes with cold, and everything mixes together, and mixtures. Mixtures increase entropy. Right? So whenever there's a transaction, entropy increases. And we've talked about this. Now let's model this in our context. Let's model this closed system as a time homogeneous first order Markov chain or Markov process, whose states are governed by this transition matrix, probability of x1 given xn, xn plus 1 given xn. Okay. And let's say that x of n is our random variable, which sort of, and we can talk about the entropy of that random variable at time n. Right? And we can talk about how that entropy changes from one time to the next. So we've got a Markov chain, so we've got a random variable at each time. And the relationship between this Markov chain, the collection of random variables, and the Markov chain is governed by two things. One, what the initial distribution was, or what the distribution is at a particular time, and then how the transition matrix, the transition, or the dynamics of the Markov process evolve. And so what we want to do is then ask, in this context, does the entropy always increase? Does h of xn always increase? So we can actually ask. So what's your guess? So based on statistical physics, do you think that we're going to see that h of xn is going to be monotonically non-decreasing? If you'd rather me not ask questions and just lecture, or
So what's the experiment for xn plus 1?
They're governed by the Markov chain transition matrix. So it's just a Markov chain, right? And we have a random variable at time n, a random variable at time n plus 1, which is related by the transition matrix and the state that xn was in. And so we can actually we can compute the marginal probability distributions over xn at each time and figure out. So given let's do this. Like we've got two starting distributions, Pn of xn and Qn of xn. So let's say that these are just two potential starting configurations at time n. And what we're going to show is that this Kovac-Ladler divergence won't increase in n. It can only stay the same or decrease. And in order to answer this question, this thing, we're going to, and this should be a question here. In order to answer that question, we're going to look at this. Okay, so how do we look at this? just as a notational shorthand, we're just going to write P of x of n for Pn of x of n. So what this really means is the distribution under P at time n of this random variable, and this is the distribution under Q of x of n, the nth random variable under distribution Q. So just to make sure that notationally we're clear. So to get the joint distributions between two successive random variables under P and Q, well, we start with the P distribution at time n, and we multiply it by the transition. And so we get the joint distribution, xn and x plus 1 under P. And we start with the Q distribution in the case of Q, but it's the same transition matrix, right? So the dynamics are the same. We're just starting with, it's kind of like if you have a Markov chain and you start it with two initial conditions, you can think of P and Q as the initial conditions, right? And then you run the Markov chain, see what happens. So we've got two Markov chains, they're exactly the same transition matrix, but we started at different spots. What's going to happen to that distribution as we keep running it? It's going to get closer, going to get far away. We're going to see that it can't get farther away from each other. So it's the same dynamics. The same dynamics means that this stuff is the same. Well, we're just starting from two initial conditions. So let's then use the chain rule of Kullback-Leibler divergence. Now we're going to start using these tools that we spent time building. And so we start with this thing, which is the Kullback-Leibler divergence between the marginals at time n and the Kullback-Leibler divergence between the two conditionals, which we know is going to be this has got to be
that should be 0.
This should be 0. Has to be 0, right? Because we just said it was 0. Right? It's the same probability distribution. So then we can also write it this way. It's just using the chain rule the other direction. Okay. So we've got this guy. And what do we know about this? Is it equal to 0? It's the reverse time dynamics. Well, do we need it to be equal to 0? Remember that it's almost the same proof as the data processing inequality. How about if we just say that it's greater than or equal to 0? Which is, we know that. So once we've got that, then we right away say, well, that's greater than 0. It must mean that this is less than that. So therefore, that as time is going forward, the two distributions are approaching each other. Or at least not going farther apart in this KL divergence sense.
But shouldn't the reverse dynamics also be the same?
No, and nor do we need it to be. I mean, it's not going to be 0. I mean, it's actually very simple to set it up. If you go back to this thing, this equation here, this is the joint distribution. If you look at if we from this take the probability of xn given xn minus 1, which we can do, and divide, they're not going to be the same in general. Because they're going to involve Pn and Qn, which could be they could be completely different. Right? Look at this joint. So the probability of xn plus 1, so probability of xn given xn plus 1, this guy could put mass on just one variable and nowhere else mass. And this guy could put mass on one value and nowhere else mass. So they could be completely different. They could be very, very different. Because, remember, so let me just write that down in case that's not clear. So, in other words, you have the probability of x of n given x of n plus 1 is equal to the probability of x of n plus 1 given x of n times p of n, x of n, divided by what? I should probably prime this variable or something. Right, so that, and then we do the same thing for q of x of n plus 1. So this is not equal. those two guys are not equal to each other in general. So therefore, this could very well be strictly greater than 0 sometimes. But that's okay, because all we need it to be is greater than or equal to 0, and we get what we want, which is that these distributions are decreasing, or they're getting closer to each other.
Wow, so the irreversibility of time comes actually from the actual probability distribution of the dynamics.
Sorry, say again?
The irreversibility of time actually comes from the dynamics itself, in some sense.
I'm not sure exactly, because if P and Q were the same, then it would be reversible, right? So
Yes.
the dynamics are different in the reverse time. So, but let's sort of go with where we're going, because what we want to do is see what happens to these two Markov chains as we're going forward in time. So first of all, we're saying that the two probability distributions, Pn and Qn, are only, if anything, decreasing or getting closer to each other as time evolves. That's equation 4.11. Now let's say that Q is a stationary distribution of the Markov chain, okay? Which all Markov chains have at least one stationary distribution. And so that means that if we apply the dynamics, we get back the same thing. So what this means is that P of xn may or may not be a stationary distribution. Let's say it's not a distribution, but what it's saying is that Q is not changing over time, right? Because Q is stationary. What it's saying is that P can only get closer to a given stationary distribution under the same dynamics. And if there's only one stationary distribution, then we know that it's going to get close, it's going to eventually hit that one stationary distribution. Right? Yep.
So Q and P actually are the initial distribution, right?
You can think of them as the initial distribution, but they're also changing over time, right? So P of x of n, it's a function of n, so it's changing with time. N is the time variable.
So if I understand this result correctly, this means that as we advance in time, then we're more likely to mistake the initial distribution with other. Right?
Well, no, but the initial distribution is fixed. That's just sitting there. Let's say it's time 1. We start the Markov chains at time 1, and then we start running the Markov chains. So at each time, we've got a new marginal distribution for the random variable at that time. And the question is, if we take, so we've got the version, let's say we've got the Markov chain that started with P at time 1, and the Markov chain that started with 2 at time 1. So it started with Q at time 1. And what we're calling at time n, we're still calling it P and Q, but it's what happened to that Markov chain after we started it with either P or Q, after we run the Markov chain some number of steps. And the question is, the corresponding marginal distributions at time n, are these guys getting closer to each other as time goes forward, or farther apart? And what this is saying is that they're getting closer to each other, if anything. They're not getting farther apart, is really what it's saying. They could be staying the same, but they're definitely not getting farther apart because of the direction of the inequality. And this is saying, in fact, if Q happens to be a stationary distribution, Q doesn't change at all. Because if we start the chain at a stationary distribution, then Q is going to be the same at every time.
Is this regardless of being ergodic or non-ergodic Markov chain?
This is a first-order Markov chain. It's basically saying that it's time inhomogeneous. We're not even mentioning the ergodicity at all. We're just basically saying it's a simple first-order time homogeneous Markov chain, and we're initializing it in a stationary condition. In this particular case here, which is the stationary distribution of Q, and P is some other initial distribution. And this is saying that over time, P is going to approach Q, and this is consistent with what we know. I mean, if we have a Markov chain and we start it with an initial condition and we keep running the Markov chain, eventually it'll hit a stationary distribution. Eventually, and that's what this is saying. And if there's one unique stationary distribution, which there is in certain cases, then it will eventually hit that one. So what we're interested in is whether or not the entropy is bound to increase, right? If, in the same sense of the entropy in statistical thermodynamics, is claimed to be bound to increase.
So there is only one stationary distribution for Markov chain.
Sorry?
So there is only one station.
No, I'm just saying this is, let's say that this is a stationary distribution. Any stationary distribution this is true for. You can never move farther away from a stationary distribution in the KL divergence sense. That's what this is saying. And what it is saying is if there's only one stationary distribution, you're going to move closer to it. Or at least you're not going to move farther away from it. But chances are you're going to move closer to it. And you know from your stochastic processes that you're going to be moving closer to it. And you get that by doing the eigenfactorization and show that the eigenvalues all that are less than 1 actually go to 0, and you've got one eigenvalue that corresponds to the eigenvector of the stationary distribution. You eventually get there, and you get there very quickly too, exponentially, because these other eigenvalues are dying down exponentially fast. All right? And so suppose the stationary distribution was the uniform distribution. It's very easy to set up a Markov chain that has a stationary distribution, a unique stationary distribution that's uniform. And so in such case, then basically it's saying that this Kullback-Leibler divergence is can be written in this following way. So it's basically the negative of the entropy plus log n, and that's going to be greater than or equal to the negative of the entropy at time n plus 1 plus log n. So what this basically means is that the entropy, since the log n is constant, the entropy is going to be increasing over time. When the uniform distribution is a stationary distribution, or especially is the stationary distribution, the entropy can never decrease. That's the depressing news, as expected in statistical physics. But the not so depressing news is suppose the stationary distribution is a non-uniform distribution. In fact, let's say that stationary distribution is just a zero entropy distribution. Then it says the same thing. It says that the entropy of the Markov chain can decrease over time, because you're approaching the entropy of 0. You're approaching the certainty distribution. So it's like approaching a singularity. Going back to statistical physics, it'd be like a repeated Big Bang, where all the energy in the universe collapses down to a single point again. And the next, maybe that's what we are. The universe is a bouncing ball, 3-dimensional ball or something, 4-dimensional ball. So, hence, the increase or decrease of the entropy over time is entirely dependent on the dynamics of how we set up the problem. So it doesn't necessarily, in information theory and stochastic processes, we don't need the entropy to always increase. That's the moral of the story. Okay. Questions on this? Okay, let's push on. The next topic we're going to talk about is information theory and sufficient statistics. Now, you might wonder why we're talking about these things before we actually get into sort of the nuts and bolts of communications theory and compression, because we're going to see how entropic quantities are very, very useful in the context of philosophy or statistics or combinatorics or probability. It's in many cases possible to come up with combinatorial bounds of problems. There's a field of mathematics called combinatorial enumeration, and that's a study of counting how many ways objects can be in a particular configuration. And there's lots and lots and lots of problems associated with that. In some cases, you can actually come up with bounds on these enumeration problems using entropic quantities by essentially treating them as a probabilistic quantity and taking things like expected values, and then entropy is an expected value, and sometimes you can do the same thing with probabilities. And we're going to do that. It's really interesting. It's really, really interesting that this can happen. So information theory is useful for many, many problems. So let's start by seeing how it relates to the notion of sufficient statistics in the field of statistics. And so let's say that we have a collection of random variables, and for the sake of this discussion, let's say that they're Bernoulli IID coin tosses with some probability of heads being theta. Okay? And let's design a statistic that counts the number of heads in that sample. Okay? So the statistic can be random. I mean, if it's a function of the random variables, then it's a random variable itself. If it's a function of a sample that's been fixed, then it's a fixed statistic. And we'll make that distinction clear depending on whether or not the statistic takes either uppercase or lowercase random variables. So t is a statistic of the sample. And a statistic in general is some function of a collection of random variables. It could be like the empirical mean or the empirical variance or the max, or it could be a sort, or you can do all sorts of things with statistics. So it's a statistic in general is itself a random variable. Note that this is a function of a collection of random variables right here. Right? And so therefore this function here has a mean and a variance itself, right? So good statistics in general, as we will see, tell you something about the sample, some property of the sample. And bad statistics don't. Like, for example, if t of x1 just gives you back x1, it's completely ignoring most of the sample. And as n gets big, it tells you not very, very little about the sample. Right? So in general, you want statistics that sort of use everything about this, some information about this sample. Statistics are also used in pattern recognition, machine learning. Sometimes they're called features. You extract features from some data. Any sort of deterministic processing that takes a signal and constructs features in either an image or an audio signal or any kind of radar signal or anything can be thought of as a statistic. Now consider the previously mentioned statistic, this counting statistic. So it just counts the number of heads. And let's condition on that statistic. So we have the probability of this sample, x1 through xn. So the probability of this sample, x1 through xn, given the statistic, which is this part, and the parameter, which is this part here. Okay. Now what we're going to show is that this is equal to the probability of the sample given just the statistic. So I should try to use the same colors here. It's equal to the probability of the sample given just the statistic, meaning what this essentially means is that the true probability of heads doesn't any longer matter. And that probability is governed by this quantity. It's just basically 1 over n choose k. Whenever the sum for I is equal to, I is equal to 1, n of x phi is equal to k, and is equal to 0 otherwise. Okay? So nowhere is there theta any longer. So the statistic has rendered, like once we've counted the number of heads, the probability changes quite a bit. It's basically equal to, how many times is there of choosing k out of n times? That's n choose k. And basically it's every instance of those has the same probability of getting k ones. And otherwise it's 0. So let's see, we're going to prove why this is true in a minute. But before we prove why that's true, let's sort of talk about what the statistic has done. So once we know the statistic, the probability of the sequence is expressible without referring back to the underlying parameter governing the random variables, theta. So you got a biased coin flip. Right? Once we know how many heads there are, in some sense, when we flip a coin n times with a biased coin, once we know how many heads there are, the bias doesn't matter. In other words, we can write this as a conditional independence statement. We can say that the sample is independent of the parameter given the statistic. And this is basically treating the parameter, usually the parameter is a constant. This is sort of thinking of it as in a Bayesian framework where the parameter is itself a random variable. But that's okay. You can think of there's some distribution over the parameters, and we first sample from that distribution over parameters, we get a bias, and then we flip the coin some number of times. The question is, the sample normally does tell us something about the bias. If you flip a coin some number of times, and you can get information about the bias of a coin by counting the number of heads. But once we've counted the number of heads, there's no more information that the sample has about the bias. So what this then means, once we have this conditional independence relationship, is we have Markov chain. Let's just call this Markov chain A. That we have the parameter, the statistic on the sample, and the sample. So the statistic renders the parameter independent of the sample. But on the other hand, we know that the statistic is a function of the sample. The statistic is just counting the number of heads. So the statistic has to be a function of the sample. So we have this secondary Markov chain, which is in some sense obvious, which is that, well, the sample is governed by the bias, the parameter, and the sample renders the statistic independent of the sample, of the parameter. Because once we've got the sample, the statistic is not going to tell us anything about the sample. The statistic is just a deterministic function on the sample, just like in the data processing inequality. So we've got one Markov chain, A, and by the data processing inequality, we know that the amount of information that the statistic has about the bias is an upper bound of the amount of information that the sample has about the bias. We have the secondary Markov chain, B, and from the data processing inequality again, we have that the amount of information that the sample has about the bias is an upper bound of the amount of information that the statistic has about the bias. Right? So then when we look at A and B together, we look at both of them, what it essentially means is that these mutual information quantities are identical. So what this means is that there's a certain amount of information that the sample has about the parameter. This is saying that no information is lost about the parameter when we use only the statistic. In other words, that the statistic is sufficient for finding out everything we can possibly find out about the parameter. And therefore, why it's sufficient, so therefore we call it a sufficient statistic. It's sufficient for finding out everything. Oops. And this is the definition of a sufficient statistic. So now, this is a very unusual definition of a sufficient statistic. Right? This is the information theoretic. If you were to take a statistics class, this would not be how you would be introduced to sufficient statistics. However, we're defining it this way. And we'll see in a moment that it's identical to how it's defined in statistics classes. So we're saying that it's sufficient for parameter theta govern the distribution F if the statistic renders the sample and the parameter independent when you're conditioning on it. So basically this is just saying that Markov chain A holds. Markov chain B always holds. Right? The question, the definition of sufficiency is that A holds. B is always true. Yes, question.
Is T taken on average or what sample?
Well, in general, T can be any statistic. In our example, T just counts the number of heads.
What sample?
No, so remember, it's a function of a set of random variables. So we have a set of independent IID random variables, and we're interested in getting information about the underlying parameter theta. These are IID random variables, but there's some underlying parameter theta that governs these IID random variables. And so the statistic is a function of a random variable, so it's a random function. The statistic is a random function in this context. Everything's a random variable here. X, which is the sample, is a random variable, or random vector. Theta is random, and then T, because it's a function of capital X, is also random. But this is in general true. I mean, if you take a particular sample, if you take a sample, then the statistic becomes deterministic. Right? I mean, it's a deterministic function of a random variable, so it's random. A deterministic function of a random variable is a random function, right? It's a random variable too. So sufficient statistics are used to estimate parameters of the data. The reason why is because once we know the statistic, we can then get a good estimate of the parameter, and we don't need to go back to the data. And there's this notion of consistency where you can get exact estimates of the parameters if you get enough data. So here's the traditional definition of sufficient statistic. So we say that T is sufficient for theta if the probability P of x and theta can be written in the following way. P of x of 1 through n given theta is equal to, there exists functions g and h such that this is true. Now, how does this possibly correspond to what we had before? So let me give you a hint before we even go on, which maybe I should have written in the slide. If I write it as h of x, 1, n, and then t, let's call this h prime. So I can define h to be equal to this thing, right? And h of x is equal to h prime of x comma t of x, right? That's a perfectly valid definition of x, right? So if I write it in this bottom way, does anyone see similarity to how we've defined it? Let's go back a page. X is independent of theta given t of x. X is independent of theta given t of x. So this was our former definition, this is the new definition. What's the correspondence? Well, correspondence is in the next bullet point, is what's the definition of conditional independence? Well, we're writing this thing down, this sort of vertical bar. I mean, what does this mean? Well, for our YouTube listeners, I'm pointing to this. What does this mean? Well, it means this. The definition of conditional independence means that A is independent of B given C if the probability can be written in the following way. If there's two functions, g and h, such that the probability can be written as g of AC and h of BC. So C is the common thing. C is the thing that we're conditioning on, and that's common to these two expressions. And notice that when we write this in this other way, g of t theta, h prime of x t. So t is the common thing. T is what we're conditioning on, which renders x and theta independent. So it's just basically the definition of conditional independence. So it's just like our Markov chain. It's Markov chain A. So we haven't really changed the definition. We've just disguised the definition of sufficient statistic. So here's how we do it. I'm not going to go through this, but I think you get the idea. You just set A, B, and C to this, and then we get this as equal to that. And then we can just write this function, h prime. If h prime of B, it's still a function of B, right? I mean, it's just, if h internally uses t, that's fine. It's still a function just of B. So anyway, if you look in the statistics book, 4.15 is exactly how you see it. And that's how they're the same. Now, let's also define something called the type of a sample. The type is something that's very, very important. It's a type of statistic. Now, let's say that we've got a collection of random variables, a collection of n random variables. Let's just, for the sake of argument, it might be binary, but let's say it's d-ary. That means it has d possible values. So each random variable is an alphabet of size d, where d is the size of the alphabet, and the alphabet might be A1 through A sub d. Okay, so what is the type? Does anyone know what a type is? Let's define a statistic. So we've got a sample. And again, statistic, if it's a function, if it's a function of a collection of random variables, it's a random value. If it's a function of a particular set of values, it's a deterministic value. But in this particular case, let's zoom in on the left-hand side. This is a lowercase x here. So right now I'm defining it using lowercase x, which means x is a lowercase. But I could easily put an uppercase x there, and that would be a random function. But let's just use the lowercase for the moment. Okay? So what this is really just, it's the empirical histogram. Right? It's basically, everybody knows what a histogram is. And what you do is you sort of count how many times each value has occurred in the sample, and you divide by the total number of samples. So it's a histogram. Probability distributions, histogram. Now we're using this notation, n's of ai given x of 1. This is basically the number of times that symbol ai has occurred in this sample, where ai is one of the alphabet symbols. Okay? Now this is the definition of the type. The type of a sample is its empirical histogram. The type of a sample is also a statistic. If we get a bunch of IID random variables and we construct the type, we've got a random histogram. The probability distribution is itself random. We've got a random probability distribution. That might sound a little bit weird, but that's certainly well defined, right? There's nothing wrong with a random variable being a probability distribution, right? It's also a statistic since it's a function of the sample. And the question is it sufficient? What do you think? Well, let's find out. Let's just use Ni as a shorthand. So Ni is basically the number of times that AI has occurred in the sample. So our claim is that this is going to be the probability. If we look at the probability distribution of x of the sample, given the statistic, and theta, the underlying governing probability, we get equation 4.18. So basically it's saying that it's if Ni, which is the number of times the ith symbol has occurred, is equal to n times the histogram at position I, then and that's true for all I, then the distribution is 1 over the multinomial choose function. N choose N1, N2, Nd. Now, by the way, this is exactly the same as what we saw before in the binary variable case. This is just the D array version. And I said, where does this come from? And I said we would prove it, and actually what we're going to prove is this more general version here. It's not even much of a proof, it's just showing that it's true. And so therefore we can see that theta is nowhere to be found in the right-hand side of 4.18. And so therefore we get 4.19, which is that it's the probability of x given the statistic. So therefore it's sufficient. Because we've got the Markov chain. Given the statistic, x and theta are independent. Given the statistic, x and theta are independent. So the other thing that's kind of interesting is that conditioned on the statistic, all samples have either probability 0 or the same non-zero probability. Now the same should be taken with a little bit of a grain of salt because it's the same up to the number of times each symbol occurred in the sample. But this is sort of all well known. Like if you flip a coin 100 times, every instance of a possible coin flip 100 times that has 15 heads and 85 zeros has the same probability regardless of where those heads lie in that sequence of flips, right? So what really matters is not where the sequence of heads live. What matters is how many heads there are in the sample. So we saw in the binary case that it's sufficiency of the type. Now the question is, how do we get this this probability? How do we derive it? So let's look at the joint probability distribution of x, t, and theta. So we can write this in the following way. So it's the product over all a in the alphabet of the probability of a raised to the number of times that a has occurred in the sample. Does everybody agree that this is the valid probability? This bit here. I mean, in some sense, it doesn't matter where each of the a's occur. We're just raising that to that power. How often it occurs in the sample. Okay. In the binary case, we can write as p0, probability of 0 raised to the number of times 0 occurs, times p, the probability of 1, times the number of times 1 occurs. So now let's consider this event. The event which is the sample and that the statistic is equal to k, where k is the true number of ones, is the same as the event x, right? Basically when k is true, when k truly counts the number of ones, then that doesn't sort of change the event. But on the other hand, when k is not the true number of ones, this event here has a 0 probability. Because we can't have a sample that has, say, 3 ones, and also the statistic of the sample say that there's 4 ones. That's an impossible event. Those are incompatible events. That has 0 probability. So that means the following. That we can take this marginal, so that when we take this joint distribution, we sum over all possible sequences. What we want to do is construct the marginal over theta and statistic equaling k. So the marginal of this, right? So now we're summing, the only thing that's not present is this. And we can sum over all x that have t, the statistic equals k, because all the other ones have 0 probability, right? So any sample that doesn't match the statistic is going to have 0 probability. But how many, basically all of a sudden, all of these essentially have the same probability. We know that, well, if there's exactly k ones, then we've got this probability. It's like the probability 1 to the k and the probability 0 to the n minus k. And then how many of them, how many instances of binary sequences are there with k1? So we'll just choose k. So we get this formula here. And so now look at 4.20, 4.23. We have everything necessary in order to derive the conditional probability. The joint probability is this. The marginal probability is this. And so therefore the conditional probability, which is the ratio of the joint to the marginal, is 1 over n choose k if the sum of y is equal to k and is equal to 0 otherwise, just by dividing. The probability itself cancels out. And the probability, this is where theta was. It's in all this stuff here. Theta was in there. Theta cancels out. Therefore, the statistic is sufficient. Okay, any questions? So there's a notion of a minimal sufficient statistic. So a minimal sufficient statistic is a function of every other sufficient statistic. So it's still a sufficient statistic, but it's minimal in the sense that you can get it by looking at any other one. So it sort of, in some sense, has the minimal amount of information about the sample while still being a sufficient statistic. So by defining the definition of t being minimal, so we get this Markov chain here. So we've got the parameter, the sample, any other statistic, and the minimal one, right? It's a function of any other one, just by the definition. And interpreting this in terms of the data processing inequality, on the other hand, says that we actually have this. It's a sufficient statistic, but being that it's minimal, it sort of renders any other sufficient statistic independent of the parameter. The minimal sufficient statistic, since it's sufficient, still, no other statistic is going to tell you any more about the parameter. In fact, all statistics have this property, but on the other hand, there's this minimality property. It's the smallest one. It's the one that's a function of everything else. And once you know one statistic about sufficient statistic about the parameter, no other one's going to tell you anything more about it, so it's going to be independent, right? So therefore, the minimal sufficient statistic is basically the least amount of information about the sample that tells you everything about the parameter. Okay, that's just, again, we can then look at this. This, you might need to think about this a little bit. But I would then, it's one of these things you just have to think about for a while, if it's not clear.
I don't understand why it's called minimal. Is that like an order or something?
It's called minimal because, let's say that you have, so a minimal one is a one that's a function of any other statistic. So kind of like, let's say that you, like here's one, like counting the number of heads. Like one statistic might be to take the sample and sort the sample, where the heads go first and the tails go second. So that's a statistic, right? That tells you everything about the sample. In fact, you've lost nothing about the sample with regard to the number of the parameters, but it's not minimal because all we need, you could do another statistic which just counts the number of heads and some reordering or reshuffling. That's a sufficient statistic, but it's not minimal, right? A minimal sufficient statistic is one that's a function of every other statistic. It's one that can be derived, and so in some sense, because it's a function of anything else, it has the least amount of information about the original, about the sample, while still being a statistic, still being a sufficient statistic.
Does it have to be unique? I mean, you can have like two minimal statistics which are both functions of each other. And
it doesn't need to be unique in general. I mean, I think, like, for example, if like if you had 3 times the statistic, minimal statistic, like 3 times the number of heads, you could, if you just know it's 3 times the number of heads, it would still be a minimal sufficient statistic. But 3 times the number of heads and 1 times the number of heads are in some sense equivalent, right? Whereas sorting the coins is not equivalent to the number of heads. Or another statistic would be the number of heads and the number of tails. Right? The number of tails is redundant.
Yeah.
The number of heads is minimal. The number of heads and number of tails is 2 numbers. It's not in some sense minimal. Although maybe that's actually minimal too. Because if you know n, then you can get back the number of tails. But I think the sorting one is a better example. So. Okay, so let's now start talking a little bit about communications, and this will, for those people who are interested, who's actually in communications? Okay, I'd be curious. I mean, one of these days we should do a survey to find out why you're taking this class. I mean, I can't imagine. I think the whole university should be taking this class, but of course, what do I know? Let's talk a little bit about communications and something that we're going to be using quite a bit, which is Fanner's inequality, which is really, really important. So let's say that we have some information source X. And again, by information now, we're really talking about entropic information, entropy. And we send X through some noisy channel, which is modeled by a conditional probability distribution, P of Y given X. And we do some further processing, G. And we get X hat. So X hat is an estimate of X, right? Now, in error, we can say that what we want X hat to be is X, and so therefore, if X is equal to X hat, then there's no error, and if X is equal to if X is not equal to X hat, then we get an error. So we're just an error if they're not equal, and we can talk about the probability of error, which is PE, right? And now, what we're going to see is that the conditional entropy should tell us something about the error possibility. So in other words, suppose it was the case that once we've got Y, then we can know X exactly. If it's possible that given Y we know X, shouldn't that mean that the error should be low? Or would it mean that the error is necessarily high? No, it doesn't. Because if we can know x from y, if y hasn't lost much of x, we should be able to do this with reasonable high accuracy. On the other hand, suppose that this is large. Suppose that knowing y, there's a lot of residual uncertainty about x. So we've lost a lot of x. That's a very, very noisy channel. When the channel is very, very noisy, we've lost information about x. And would this mean that the error is high? It should be. So what Fano's inequality does is it allows us to come up with a more formal relationship between these two quantities, the conditional entropy and the error. And here's Fano's inequality. We'll just state it. Let's take a moment to digest it. It basically says that the entropy of the error probability plus the error probability times log of the alphabet size minus 1 is upper bounded by this conditional entropy, which is further upper bounded by the secondary conditional entropy here. First thing to note is that when the probability of error is equal to 0, so that means that the entropy, this first entropy is 0, the second term is 0, so it's basically saying that the conditional entropy is equal to 0. So that means that the probability of error equaling 0 requires that the conditional entropy be 0, meaning that y tells you everything about x. So it's a necessary condition for 0 probability error, which is makes a lot of sense, right? Should make a lot of sense. We can weaken the theorem a little bit by let's upper bounding the entropy to 1 and get rid of that minus 1. And we get this form. Or we can get a lower bound on the probability of error here. So basically we're seeing that some function, monotonic function of the conditional entropy is a lower bound on the probability of error. And as the conditional entropy goes up, the probability of error, if anything, can go up. Can only go up. At least the lower bound of it goes up. So ultimately what we're going to do is use Fano and various versions thereof to prove Shannon's coding theorem. And what this is going to, actually the converse of Shannon's coding theorem, and what this is going to do is going to say that any code that has probability of error going to 0 as the block length increases must have a rate less than the capacity of the channel. And these are all things that we're going to define. So there's going to be some critical point, which is called the capacity. And if the error goes 0, it must be the case that our rate is upper bounded. But first of all, let's actually prove this. So we're going to define an error indicator variable, error indicator random variable E. So E is just going to be an indicator of error. And you can sort of write this in this way. So we've got x, which gets sent to y, and then we've got some decoding process which gets back x hat, which is our estimate of x. And error is a function of x and x hat, and it's just an indicator of not inequality. And so let's use let's then bound a couple of quantities. So we've got the entropy of, the conditional entropy can be written in this way using the chain rule of entropy. Now what is this quantity here? If we know x and x hat, is there any uncertainty about the error? No. So we know that this has to be equal to 0 because we know the error is a function of x and x hat, deterministic function, in fact. And so if we know x and x hat, the entropy of E's got to be 0. Now let's use the chain rule again. And we've got the conditional entropy of E given x hat, and then the conditional entropy of x given E and x hat. So what do we get here? So the first guy we get, well, this is upper bounded by the entropy of E. Conditioning reduces entropy, so we get the entropy of E, which is the entropy of the probability of error. And the second one we're going to get as probability of log of x minus 1. Oh, why is that? That's not so bad, but let's prove it. So this conditional entropy, which is the one on the right, you can just expand it out from the definition. So it's the average of these sort of partially event-specific conditional entropies. So the probability of error is equal to 0 plus the residual entropy of x given x hat and there was no error, plus the probability of error is equal to 1 times the residual entropy of x given x hat and there was an error. So let's first of all talk about this guy. If there's no error and we know x hat, what's the residual entropy? 0. So that whole term becomes 0 here. And if there was an error and we know x hat, can we upper bound the entropy of x? Well, we have x hat, right? And we know it's not that. So that leaves n minus 1 additional possibilities, right? So that's a nice upper bound. It's n minus 1, or in this case, log of x minus 1 is the upper bound of the entropy. And then this is the probability of error is equal to 1. That's just PE. So this whole first term is 0. This thing becomes PE times the remaining the remaining maximum entropy, which is in the uniform, assuming it's uniform over for the rest of the guy. So that's a way to get this bound. This is from here. It's kind of silly, but it works, right? So now, if the error is equal to 1, we certainly know that x and x hat are not equal to each other. Oh, actually, I already said this part. So once we get that, we just use this bit. So we combine this, and this to get this bound. And then the next thing we do is we use the Markov chain and the data processing inequality. X, y, x hat. So that basically means that the information between y and x is an upper bound of the information between x and x hat. But entropy is the same. We use the definition of mutual information. The entropy minus the conditional entropy, the entropy minus the conditional entropy. We cross off the entropy part, and we get that this conditional entropy is true, and we complete the theorem. Okay. There's Fano's inequality. So these are the kinds of things that you'll be doing in your homework. I hope that these proofs seem kind of neat. So here's a summary of Fano's inequality in a one-slide summary. So again, when we have the noisy channel, and from x to y we do some further processing, this is how we relate the error to the conditional entropy. Okay. Any questions about Fano's inequality? Okay. So you know what? So I'm just going to go through this very, very quickly. I'm not going to go through the proof of this, but one of the things I said is that you can use entropic quantities to come up with bounds on probabilities. So this is you have two random variables and they're independent. The first random variable is governed by P, the second random variable is governed by R, and they're over the same alphabet. And we're interested in coming up with a lower bound on the probability of them being equal. And so we can do this by the following inequality. It's the max of 2 to the negative entropy minus the KL divergence. And maybe, just to make it simpler, I'm not going to prove it like I said, is if there are IID random variables, the probability that they're equal is less than or equal to 2 to the negative entropy of the probability. So what's interesting is that you can oftentimes, like I don't want to go through the proof right now because I want to try to get into something else. We can oftentimes go through, we can come up with bounds, upper or lower bounds on probabilistic quantities or combinatorial quantities, counting quantities, by expressions that involve the entropy. In this case, we have 2 to the negative entropy. So in some sense, the entropy is sufficient for lower bounding this underlying collision probability. And this could be very, very useful, right? Like let's say, for example, you want to maximize this probability. This is collision probability. It's like the diagonal. It's the diagonal of the joint distribution. It's summing up the diagonal. And let's say you want to maximize this, or you might want to maximize the lower bound or something. What would be the maximum instance? It just basically says what you sort of know, which is that if you take a zero entropy distribution, the entropy is 1. The entropy is 0, I mean, which is going to be 1. Right? Okay. So something else I wanted to I'm going to skip. So I talked about these different laws of modes of convergence here, and they just have a bunch of definitions about them. I want everybody to go through the slides, and there's just different implications associated with it. There's almost sure convergence. There's convergence in the R norm, convergence in probability, and convergence in distribution. You've probably seen them before. If you haven't, I've got all of the definitions in these set of slides. The point of these is just to notice that when we talk about things like the law of large numbers, or the weak law of large numbers, or the strong law of large numbers, the only difference is in this mode of convergence. How do things converge? So we're primarily going to be talking about the weak law of large numbers, which I will define in a minute. But remember that we can get from the weak and the strong by using different modes of convergence. And I want to spend the last 5 minutes talking a little bit about something which I hope to really spend all of lecture on Thursday on, which is the asymptotic equipartition property. So everyone please listen to this next sentence. Read chapter 3 before coming to Thursday's lecture. Okay? And when you're done reading chapter 3, it's a very short chapter, read it again. Okay? I'm not kidding. So this, for some reason, is always one of the chapters that people find very confusing. This is sort of a hurdle. Chapter 3 is a hurdle. Some people find it extraordinarily confusing. So read it and then read it again, because I want to spend all day. And what I want to do is begin a little bit of chapter 3 today, which is the asymptotic equipartition property. So first of all, it's a mouthful. You have to learn how to say it. Asymptotic equipartition property. Can everybody say that? Basically means that eventually everything becomes equal in a certain sense. And so what we're going to do is we're going to consider blocks of outcomes of random variables. Like we're going to petition the possible set of outcomes of random variables. So like we've got a set of n random variables, and let's say that they're IID. Okay, they could be binary, but they may not be binary. They're IID, and consider, like, let's say it's a vector of n random variables, and we can, all the possible assignments. So if it's a binary random variable, then there's 2 to the n possible assignments. And what we're going to do is we're going to partition these assignments into different blocks, meaning that it's going to be these assignments and these other assignments in a particular way that's kind of interesting. So we've got IID random variables distributed all according to P. We can also say that we could say they're binary or they're k-ary, so that there's k possible values. We'll be doing both. But in general, if it's binary, there's 2 to the n possible outcomes. In general, there's k to the n possible outcomes, right? Now, suppose we wish to encode these k outcomes using binary digits. Like, every message, like if it's English text or if it's some audio file or something, we have words, and words or characters or something, and characters might come from an alphabet of size k, but ultimately when we store them on a computer, they have to be stored in an alphabet of size 2, right, which is binary. So, and if we have a length n binary string, then there's 2 to the m possible strings that can be represented. So we have, let's say, a source message, which is, a string of length n k-ary symbols, and we have some sort of encoder. There's k to the n possible messages. There's n letters or alphabet symbols, And we have an encoder that tries to represent it in code words of length m, with m binary digits. So each one of these are binary. There's 2 to the m possible messages and m total bits. And in order for us to be able to, like in English we might have k is equal to 26. So we want to be able to code for every message. So it must be the case that 2 to the m is greater than or equal to k to the n. So the number of bits, can everybody see this? And that's where, we usually don't have this problem with sun blaring. But we have m, the number of bits, or in other words, the length of the code words, cannot be any shorter than log k over n. So let's now talk about rate. So the notion of rate is also sometimes seen as confusing. So we want to sort of define what we mean by rate. So the rate is the number of bits used per source letter. Does anyone know what that would be? So how many bits? M. How many source letters? N. So that basically means that the rate of doing this would be log k bits per source letter. So in English, what this means, if there's 26 letters in English, you need 5 bits. The seal of log k is 5. The log, again, is always base 2, unless we say otherwise. So it means that for English, we need to represent English characters using 5 bits per source letter. Right? Would that be a good code? You know, we talked a little bit about this in lecture 1. Now the question we want to ask is, can we use fewer than this number of bits per source letter on average and still have no error? Like, this is sort of a fairly naive way of coding, right? We basically say, okay, well, I've got, you know, how many, we've got, let's just go back to this picture again to make sure it's clear. We've got k to the n possible messages and 2 to the n possible code words. And so we just want to make sure that we use log k bits per source letter uniformly, irrespective of their probabilities. And we know in general that that's probably not a good code, right? Because that basically says that even if something's used very, very infrequently, we're still using log k bits. What we want to do is basically things that are very, very probable use fewer than log k bits, and things that are very, very improbable use many more. So here's an even more extreme example. Let's say that some source messages, we use fewer than log k bits. Some source messages get mapped to code words. And other source messages, in order to use fewer than log k bits, we throw them out. Meaning like they're not transmitted, they're not represented. It'd be kind of like saying, if you type a particular sentence into your Microsoft Word file and then you compress it, that sentence just happens to be one that gets tossed. So then when you look at it again the next day, that sentence is gone. And every time you type that sentence, it's gone. Is that does that seem reasonable? So it turns out that this will be perfectly reasonable. This is perfectly fine.
Because you can simplify.
No. You will have an error. Perfectly fine. If you don't like this, however, we can have another one where, let's say we do something like this. We have long code words and short code words. So some messages get sent, some source strings get sent to short code words and other ones, rather than just having an error. We're going to show that these two scenarios are identical. Whether you have an error or whether you don't have an error, as n gets big. That's the trick. N has to get big, and I'm running out of time. So sorry for the technical problems earlier at the earlier lecture. Again, read chapter 3. Think about this, right? So I'm going to say this error, this garbage throwing out some words is going to be the same as this. And this is what the asymptotic equipartition property is going to help us understand. It's really cool. This is a very interesting chapter. It's a very deep chapter. Any questions? So come early to Thursday's lecture. And again, if you want to read that chapter 3 times, that's a good thing as well. Okay, I'll see you then on Thursday.